Hello and welcome to another video for Calculus 1. In this video, we are going to discuss about another application of derivatives, which is graphing functions. So in order to graph a function, we are going to follow this guideline. So first we'll find the domain of the function, then we'll find x and y intercept. Then if necessary, we'll check the symmetry. Then we'll find the vertical asymptotes or horizontal asymptotes, if any. Okay, usually if our function is a rational function or the exponential log functions, we might have those asymptotes. And then we'll find the first derivative and we'll use that to find the intervals where the function is increasing, decreasing, and then use the critical points to find the max and mean value, okay, local max and local mean. And then we'll use the second derivative to determine where the function is concave down and concave up, and then we'll plot whatever we found so far in the graph to draw the graph, okay. So one question might be, why do we need to graph this by hand? Because these days we know that we can use technologies to graph a function, but the goal of this section or this video is to graph a function by hand so that we will put everything that we'll have learned so far, like finding critical points, using first derivative to find the intervals where the function is increasing, decreasing, finding local max and mean, and then finding the critical, inflection points, concavity. So we'll use calculus to do those things, and then putting them into a graph would help us to really understand things that we have learned so far. So that's the main goal of graphing function using these things. Okay, so let's look at an example. The first example, we don't have any particular function. What we have here is it says any random function. Okay, we are given any random function, but we are given this properties. The first one is it says the function, the first derivative of the function is negative, which means the function is decreasing. Okay, so this means the function is decreasing. And here it says the second derivative is negative, which means the function is concave down. And in another interval, it says the derivative, again, the first derivative is negative, which means decreasing. And this one says the function is concave up. So let's just draw this random graph. This is not any particular function, so there's no any like unique or particular answer for this one. Okay, you can have different graph for this one. So our interval is the first one is from negative infinity to 2, and the second interval is 2 to infinity. So I'll just put 2 here. So on the left of 2, the function is decreasing and concave down, so it should look something like this. Okay, and I'll stop here. And then on the right of 2, the function is still decreasing, but it is concave up, so it might look something like this. So that's how the graph looks like. So this is x-axis, this is y-axis. Don't forget to label the graph. So yeah, that's how this one looks like. Again, there's no unique answer for this one. It is any random function. You could get a different graph, okay, than what I have here, but it looks something like that. So now let's look at the first actual example of graphing. This is a polynomial function. So we'll go ahead and graph this one, and then we'll look at one more example where we have a rational function. So the first thing that we need is the domain. Okay, so this is a polynomial function, so you know that the domain of this function is all real numbers. Next one, let's go ahead and find the y-intercept. So usually in a polynomial function, the constant term represents the y-intercept, or when you make x equals 0, you get 3. So that is the y-intercept. So the y-intercept is 0, 3. Now let's find the x-intercept. To find x-intercept, we are going to let the function equals 0. So 1/3 x cubed minus 1/2 x squared minus 2x plus 3 equals 0. Now, just to get rid of that fraction, I'm going to multiply everything by 6, okay? So if I do that, then I get 2x cubed minus 3x squared minus 12x plus 18 equals 0. Now we can factor this by grouping, so we'll group these two together and these two together. So from the first one, we can factor out x squared. So if I factor out x squared, I get 2x minus 3 minus, from the second one, if I factor out 6, I get 2x minus 3 equals 0, or that becomes 2x minus 3 times x squared minus 6 equals 0. So from here, we'll get x equals 3 half, and from here, we get x equals plus or minus square root of 6. So our x-intercepts are 3 half, comma 0, and then we have square root of 6, comma 0, and negative square root of 6, comma 0. Okay, so these are the x-intercepts. So now next, we don't have any horizontal or vertical asymptote because this is a polynomial function. So we'll go ahead and find the first derivative of this function. Okay, so the next one is we'll see the first derivative. So a prime of x equals, so bring that 3 down, cancels with this 3, so we get x squared minus x minus 2. So that's the first derivative. We'll use first derivative to find the critical numbers. So there's no point where the derivative is undefined because it's still this is a polynomial function, so it's defined everywhere. So we'll set the derivative equals to 0 to find the critical numbers. So x squared minus x minus 2 equals 0. We can factor this. So we have x minus 2 times x plus 1 equals 0, which gives us x equals 2 and x equals negative 1. So let's do the sign test to determine whether the function is increasing, decreasing, or constant, or whatever we have. So let's draw this number line. Let's put those critical numbers, which is negative 1 and 2 here. And let's do the sign test. So basically what we do is, this is the first interval from negative infinity to negative 1. And the second interval is negative 1 to 2, and the third interval is 2 to infinity. So we'll pick a point from each interval, a number from each interval, and we'll plug that into our first derivative. So if it is positive, the function is increasing. If it's negative, the function is decreasing. So from the first interval, let's go ahead and pick negative 2. And if I put negative 2 here, so negative 2 squared is 4 minus negative 2, means 4 plus 2, which is 6, minus 2 is 4. So it's positive here. Similarly, from here, if I pick 0, so 0 squared minus 0 minus 2 is a negative number. From here, again, if I take 3, so 3 squared is 9, minus 3 is 6, minus 2 is positive 4, so it's positive here. So the function is increasing here and then decreasing, decreasing, and increasing. That means we have local max here and local mean here. So which means we have local here, local max, and then we can find local max by putting this negative 1 into our original function. So if we do that, if we take that negative 1 and put it into our original function, we are going to get 25 over 6. Similarly, we have local mean here at 2. So if you take 2 and put it into your original function, we get negative 1/3. Sorry. So negative 1/3. And in decimal, this is approximately 4.167. This is approximately negative 0.33 repeated. Okay. Now let's go ahead and find the second derivative. So the next thing is we're going to find the second derivative, and we will use the second derivative to figure out whether the function is concave up or concave down. Okay. So the second derivative equals the derivative of this function here, which is 2x minus 1. So to find the inflection point, so we'll do 2x minus 1 equals 0. If we solve for x, we get 1/2. Again, we are going to do the sign test for this. So let's draw the number line. So our point is 1/2. Now if I pick a number on the left of 1/2, which is 0, let's take 0 and put it into our second derivative, we'll get -1. So it means this is negative. So the function is concave down in this interval. And here if I take 1 and put it over there, I get 2 times 1, 2 minus 1 is 1, positive 1. So this is positive, which means the function is concave up here, okay? So one more thing that we might need when we graph is, we know that the x value for the inflection point is 1/2. So what is the y value? So we need to find that. So we'll take this 1/2 and again put it into the original function right here. So if we do that, we will get the value of y as so approximately 1.91. Okay, so we can use calculator to find that. So we'll take 1/2, put it into the original function. That's what we are going to get. So now I think we are ready to graph this function. Okay, so what we are going to use is, we are going to use the y-intercept, the x-intercepts. Then we are going to use this local max and local mean, okay, right here. And then we are going to use the inflection point. One more thing we might have to do here is, we have a square root of 6. So what does that exactly look like? If we change that to decimals, it's approximately 2.45. We might need that. So let's go ahead and graph this in the next slide right here. So let's go ahead and draw the x and y axis. So I have my y axis here, and then this is the x axis. So this is x, this is y. So I'm just going to take this as 1, 2, 3. So I'm not going to label it. I'm just going to take the grid as it is. So if we go back, the first thing is, what is the y-intercept and x-intercept? So y-intercept is 3. So let me take a different color. So y-intercept is 1, 2, 3. So here's the y-intercept. And then x-intercept is negative square root of 6 and positive square root of 6. So square root of 6 is 2.45. So 2.45 means somewhere here, and then 2.45 somewhere here. Those are the x-intercepts. And then let's look at max and mean. So we have local max at -1, which is 4.167. So at -1, so 3, 4, somewhere here, local max. And then local mean is at -2, and it's -0.03, so somewhere here. That's the local mean. Then we have inflection point at 1/2 and 1.9, which is almost 2. So inflection point is at 1/2 and then right here. So on the left of 1/2, the function is concave down. On the right of 1/2, the function is concave up. So let's go ahead and draw this function. So here the function, so it comes this way. The function is concave down all the way to this point. From here, the function is concave up. So basically, that's how it's going to look like. It's just a little bit simpler. The next example is a little bit more complicated, the one that we are going to look at next, okay? So here again, let's go ahead and find domain. So this requires a little bit more space, so I'm going to write really small. So the domain, so this is a rational function. So to find the domain of the rational function, we'll set the denominator equals to 0 and then see if there's any point where the function is undefined. But since we have x squared here, we are always going to get this number as a positive number. So if this is a positive number plus a positive number, so we are always going to get a positive number in the bottom. So there's no way we are going to get a 0. That means the domain of this function is all real numbers. So there's no x value that can make the denominator equals to 0. No any real x values, okay? So that is the domain. So to find x-intercept, usually with the rational function, what we do is we factor and cancel out any common factor, and we set the function equals to 0 and find the x-intercept. Okay, so basically here, so we don't have any common factors. So when you're finding, so for example, if you have a over b equals 0, then how we solve this equation is we multiply by the denominator on both sides. So we basically get a equals 0. which means here we basically get the numerator equals to 0 when you're finding the x-intercept, okay? So to find x-intercept, we take the numerator equals 0, which means 14x equals 0, and when you solve that, we get 0, so 0, 0. And then the y-intercept, for y-intercept, we said x equals 0. So here, if we take x equals 0, so the numerator is 0 divided by 3 times 0 plus 4 is 4, which is 0. So we have x and y-intercept. Now here, another thing is the asymptote. So we don't have any vertical asymptote because the denominator is never equal to 0. And then the horizontal, to find the horizontal asymptote, we just compare the degrees, okay? So the degree of the numerator is 1, degree of the denominator is 2. So if the degree of the numerator is smaller than or less than the degree of the denominator, then the horizontal asymptote is just y equals 0. So that's the horizontal asymptote. So we have this information. Now what we do is we'll go ahead and find the first derivative of this function. So let's go ahead and find the first derivative. So f prime of x. So we will use the quotient rule. So denominator, which is 3x squared plus 4 times derivative of numerator, which is 14, minus numerator times derivative of denominator, which is 6x, divided by denominator squared, which is 3x squared plus 4 squared. Now, so let's go ahead and simplify. So when we multiply that, we get 42x squared plus 14 times 4 is 56 minus 14 times 6 is 84 x squared divided by 3x squared plus 4 squared. Now, if we simplify or if we combine the like terms, we get negative 42x squared plus 56 over 3x squared plus 4 squared. Now, let's go ahead and find the critical numbers. So again, critical number is given by two things. The first one, wherever the derivative does not exist, or if the denominator in rational function, that is usually when the denominator is equal to 0. Again, this can never be 0. We always get the positive number, so there is no such cases. The next case that we get the critical numbers is when we set the derivative equals to 0. So setting the derivative equals to 0 is again similar to finding that domain or the x-intercept, which is setting the numerator equals to 0. So we take the numerator and we set it equal to 0. So negative 42x squared plus 56 equals 0. And then if we subtract 56 and divide by negative 42, we get x squared equals negative 56 over negative 42. And then that gives us x equals square. So 56 over 42 is 4/3. And then we take the square root. So that gives us x equals positive or negative 2 over square root of 3. Okay. So that is our critical number. Let's do the sign test. So we'll draw a number line. And then we have two critical numbers. So negative 2 over square root of 3. If we put this into the calculator, we get approximately negative 1.1547. Okay. And then 2 over square root of 3. That is approximately 1.1547. So now let's take a number from here. We'll take a negative 2 and we'll put it into our first derivative. Okay, so that's how we do the sign test in order to figure out the intervals where the function is increasing and decreasing. And also that helps us to determine the local max and local mean. So if we take negative 2 from here and put it into our first derivative here, so negative 2 squared is positive 4 times 42. So when we do that, we get a number greater than 56, but it's negative. So basically, we are going to get negative in the numerator, divided by, again, the denominator is always positive, which means this first interval is a negative. We get negative number here. So this interval, okay, so in this interval, the function is decreasing. Similarly, from the middle one, if we take 0 and put it here, we get 0 plus 56, which is positive in the numerator, and denominator is always positive, so we get a positive number here. Similarly, if we take a number from here, maybe 2, okay, so it's same as negative 2 because we are squaring it and we are going to get a negative number here. So this interval negative 2 over square root of 3 to 2 over square root of 3. So the function is increasing here. And then here 2 over square root of 3 to infinity, the function is decreasing. That means here the function is decreasing and increasing, so local mean here, and then function is increasing and decreasing, so local max here. So let's go ahead and find the local max and local mean. So we have local mean here, and then to find the value, we'll take this one and put it into our function right here, and that gives us approximately negative 2.02. And then local max is right here. We'll take that number, put it into our original function, and that gives us approximately 2.02, the positive. So that's all with the first derivative. Now we are going to use the second derivative to figure out the point where to figure out the interval where the function is concave up and down. So let's go ahead and find the second derivative. Okay, second derivative of this function. So f double prime of x equals, again using the quotient rule, to this quantity here. So 3x squared, the denominator, times derivative of numerator, which is negative 84x, minus numerator, which is negative 42x squared plus 56, times derivative of denominator. We have to use the chain rule, so it's 2 times 3x squared plus 4 to the 1, so we don't have to write that, times derivative of inside function, which is 6x. Then divide everything by 3x squared plus 4. We already have a square and we're squaring it, so it's a fourth power. Now what I'm going to do here is I'm going to factor this out. So that will probably help us to simplify a little bit easier. Okay, so we have 3x squared plus 4 to the square here. And then we have a same factor here. So I'm going to factor that out. So if I factor out 3x squared plus 4, then here I still have one of those factors, which is 3x squared plus 4 times negative 84x minus, so 2 times 6 is 12x times this factor, because we already factored that out, so negative 42x squared plus 56, and then divide by 3x squared plus 4 to the fourth. Now what we can do here is we can cancel one of these factors, so we get f double prime of x equals, so if we multiply, we get negative 252 x cubed minus 336x plus 504x cubed minus 672x divided by 3x squared plus 4 cubed. And then when we simplify that, we get 252x cubed minus 1008x over 3x squared plus 4 cubed. Now to find the inflection point, what we are going to do is we will take this numerator and then set it equal to 0, because taking the second derivative and setting that equal to 0 is same as just taking the numerator. So 252x cubed minus 1008x equals 0. So if we factor out 252x, then we get x squared minus 4 equals 0. From here you get x equals 0. From here you get x equals positive negative 2. So let's do the sign test to determine where the function is concave up and down. Okay, so we have negative 2, we have 0, and we have positive 2. So if we take negative 3 and put it into our second derivative, so we are going to get a negative number. So the function is concave down here. Now between -2 and 0, if we take -1 and put it into our second derivative right here, we'll get a positive number. You can try this using your calculator. Okay, so if we pick 1 and put it into our derivative, we get a negative here. And similarly, if we take 3, we get a positive here. So the function is concave down, and up. Okay, so one more thing that we might need is the inflection point. So we have the x value. So to find the y value, we take -2 and put it into our original function. And then we approximately get -1.75. At 0, we get y equals 0. At 2, we get y equals 1.75. So we might need this when we are graphing. Okay. So we have all the information that we need. So we are going to graph. So these are some of the things that we are going to use. So we are going to use the x-intercept, y-intercept, horizontal asymptote, the local max and means right here, and then we'll use these inflection points right here. So these are some of the things that we are going to use. So let's go ahead and draw the x and y axis. So this is the y axis. And then we have the x-axis here. So again, I'm going to use the grid as it is. Its division is 1. So what we have is we have our x and y intercept at the origin. So both x and y intercept right here. And then we have max at, so if we go back here, we have max, if we go back here, so we have maximum at 1.1547 and the value is 2.02. So almost at 2.02, somewhere here, okay. Similarly, we have minimum right here. And then we have the inflection points. So inflection points are, so let's go ahead and put them. So the first one we have at -2 and -1.75. So -2, -1.75, somewhere here, okay. Similarly, +2, +1.75, somewhere here, and then at 0. So the pink points are the inflection points. So on the left of this, we have the graph concave down and decreasing. So the graph should look something like this. Now from here, the graph changes the concavity and then it becomes concave up. So it goes up this way. And then from here again, it changes to concave down. So like this. And from here again, concave up. So it's something like that. So that's how the graph is going to look like. This is all for this video. I'll see you again in the next video.